we drew the Lewis structures of ozone together, and we found out that we got two structures, right? Because these are resonance structures. Now the question is, which one is the real structure of the ozone molecule? Well, it's kind of hard to explain, but let's start right here, okay? If you look at these two Lewis structure, I'm not saying that Lewis structure is correct, right? But I just want to see the reason behind it. All right, if you take a look at this Lewis structure suggests that ozone has two different structures. Yes, two different structures, yeah. And the two oxygen bonds in the ozone, they have different length, right? One is single bond, one is double bond. The other structure, the double bond on the left side, the single bond is on the right side. All right. And you can look up, you can just search Google the length of oxygen single bond and the oxygen double bond. They are different. Yeah? The single bond is longer, the double bond is shorter. So Lewis structure suggests that a structure of ozone, one bond is longer than the other. That's my point. Yeah, there's 1.21 angstrom, the other one 1.49 angstrom. Okay. However, compare this to the experiment. This is what we actually find out. Okay. So the experiment said ozone exists as a one structure. Oh, whoa. Well, of course, we have to believe the experiment. Lewis structure is just our drawing, right? Maybe it does not reflect the real ozone. But experimentally, we found that ozone exists only one structure. And both the oxygen bonds in ozone have the same length, and not like 1.49 angstrom or 1.21 angstrom. It's only 1.28 angstrom, somewhere between the length of single bond and the length of double bond. Okay, so ozone actually have 1.5 bonds, and the ozone these two oxygens on ozone have the same electron density. If you look at the Lewis structure, the Lewis structure suggests that one of them have higher electron density than the other. So three lone pairs and two lone pairs. All right. So if the other structure, 3 lone pairs on the right, 2 lone pairs on the left, different electron density. Well, so what's going on here? Well, we have to believe what we find out, right? This is the limitation of the Lewis structure. Right? The Lewis structure sometimes cannot explain, cannot represent the real structure of the ozone. Now, what's the real structure of ozone look like? Well, it's really difficult to explain, but I'm going to give you an analogy first and then draw that conclusion to what's going on in here, okay? So let's say if you want to explain what a nectarine looks like or tastes like to a person who never had nectarine before, how will you explain it? It's going to be difficult to explain, right? This person is from, let's say, Japan. He or she never had nectarine before. How will you explain it? It's going to be difficult. But this might be easier to help you out to explain this. So nectarine, nectarine tastes like peach. Looks the outside, no, the taste like peach, but the outside is as smooth as plum. Okay, and the color is somewhere between the peach and the plum. Does it make sense to you? Yeah, right. That's nectarine. It's somewhere between peach and plum, right? So the image of the peach by itself is not enough to explain what a nectarine look like. And same thing, the image of plum by itself is not enough to explain what nectarine look like. But if you put them together, you kind of get an idea what a nectarine looks like and tastes like as well, right? It's like if you imagine this picture of Chris Pine and another picture of Bradley Cooper. Put them together, you get me. Right? I'm half Bradley Cooper, half Chris Pine. Both of them is not handsome enough to explain me, but if you put them together, that's me. Anyway, now the important part is right here. Nectarine never ever vibrate every second to peach and plum. Never. Nectarine is always nectarine. Peach is always like peach, and plum is always like plum. But each individually of peach and plum are not enough and not adequate to explain what a nectarine look like, right? But put them together, mold them together, you get an idea. Oh, that's a nectarine. That's the same idea with the limitation of the Lewis structures. right? Both structures suggest that, well, this bond is long on the left side, short on the right side. The other one, short on the left side, long on the right side, right? But put them together, the length is somewhere between 1.49 and 1.21 angstrom. So that's 1.28. And both bonds have the same length. Right? Same thing with the electron density. High electron density on the right, high electron density on the left. Put them together, they share the same electron density on both sides. Okay, so Lewis structure by itself is not enough to explain what the real ozone looks like, but put these two together, you kind of get an idea what the real ozone look like. Okay, and an important part is ozone has only one structure. Ozone never ever vibrate between left and right, these two structures. Not like 1 second the bond on the left is longer than the other, and the other second the other bond is longer. No, ozone always have one structure. The two bonds here, they have the same length. Okay, all right. Now, how many resonance structures of carbonate are there? All right, so this I'm going to go quick in here, so I'm sure you can do this now. So carbon is in the middle, oxygen is around it. Now Lewis structure, Lewis symbols, carbon 4 unpairs, oxygen each one have 2 unpairs. Okay, now we're going to make we have -2 here, so don't forget. So -2, put 2 electrons onto the carbon, the central atom. So 4 electrons going to be 6 electrons. All right, now make a non-central octet first. Each oxygen needs 2 electrons, so go 2, 2, and 2. So carbon is 4. It's no more electrons left on carbon. So you get that. Now check the structure. So carbon on oxygen on the left side, 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons, happy. At the top, 1, 2, 3, 4, 5, 6, 7, 8. Also 8, also happy. On the right side, 1, 2, 3, 4, 5, 6, 7, 8. Also 8, happy as well. Now carbon in the middle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Way too many electrons here. So carbon can hold only 8, right? But that's right now 12. So we have to remove bonds. How many bonds though? 2 bonds. Right, so 12 down to 8. So we need 4 electrons removed from the carbon. So that's 2 bonds. So you can do that, right? You can do the top and the left or top and the right, right? And these are resonance structures. Right? So you can see the electron flow. You can flow anywhere in here. All of them are resonance structures. Okay. So again, Lewis structure suggests that carbonate have 3 structures, but no, that's not really true. Right? Not like one single bond is longer than double bond. Single bond is longer than double bond. So, and bonds in carbonate are not equal, not the same length. But it's not really true. Carbonate, all bonds in carbonate have the same length, about 1.5 bonds, 1 and 1.5 bonds, and all oxygen have the same electron density. Right? But put each one of them is not adequate to explain what the real carbonate look like. But put them together, you get an idea. Oh, that's carbonate. So about 1 and 1.5 bond, 1 to 1 1/3 bond. Okay, so not single bond, not double bond exactly. So the whole thing is 1, 1.5 bond. All right. So all right, let's move to formal charge. We're almost done with the